I just want to show you the laser equipment, the several features of several parts of the equipment, and later on you will have a short demonstration of different laser surface treatment processes. This will include laser hardening and laser remelting of two iron-based alloys. So I think first there's another space we can go around here. Laser beam is not switched on, so you can come here now. So what you're seeing here, that's the laser source itself. Here the electronic part and the laser cavitation are placed. Means here in this small box the laser beam is being produced. Small box. I said small box because we have in Clausthal we have a similar laser with similar output power, which has dimensions like an omnibus. So this one is 10 years younger than ours, so it's much smaller compared to our laser. So this laser type is a CO2 laser, means the laser beam is being produced by the excitation of CO2 gas. The gas or the laser is working with a gas mixture. You have CO2 as gas for the production of the laser beam itself by excitation. You have nitrogen, which helps this process to form this, how is it called, cascade of excitation reactions in this process. And the main part of the laser gas is helium. Helium simply is to be used for keeps the process cool. Helium is mostly used here as a cooling gas within. So you need a combination of these three gases to produce a laser beam in a CO2 laser. The laser beam, when it's produced, is being coupled out there by a semi-transmittent laser. So you have a thing called Brewster window there, where the laser is being coupled out. And then the beam is supplied by some guiding systems, consists of different mirrors, to the place where you need it at your workpiece. So, yeah, I think we can go over there now. I told you that we need quite complex systems for beam guiding. These beam guiding systems, in this case, consists of copper mirrors. The mirrors have to be cooled, and for example, in this case, they were plated with rare resistant material like molybdenum, for example, to protect it from scratches, from dust, from vapor from the material, from sparks or little droplets of your material. So the complete beam guiding system of this laser consists of this type of cooled copper mirrors. In normal cases, only the last mirror is a focusing mirror. The other ones, to guide the beam to the workplace, are simply plain reflecting mirrors. It's also possible to guide and especially to focus this beam by lenses. I hope this is one, I don't know. Yeah. This is a typical lens you use for focusing of CO2 lasers. It's, when I'm right, of zinc selenide. Why use lenses instead of mirrors? For example, for cutting applications. What you see here is a typical, is it a cutting nozzle? Yeah. I have to ask because I'm not really working with this laser. Cutting systems are always working with gas under pressure to come out to blow out the melt in the cutting process. So you need to build up gas pressure inside your optic system, in your nozzle system. You can't achieve this by this open mirror constructions. You have lenses being, how's it called? Sealed to build up the gas pressure, and the cutting gas come out of this nozzle system. So you find this as a general issue that mostly the cutting optics are with lenses, and all other optic systems for other applications like welding, like surface treatments are with these mirrors. Why? You can imagine these lenses are very sensitive against being dusted or something. If you have a little dust on it, the laser beam can couple on it and will you get a heating up and a thermal damage of your lenses. So the lenses are very sensitive against this. So that's why they only use it where it's protected, like in this case where you need it for the cutting applications. Otherwise, you mostly use this type of mirrors which are not so sensitive against all this things like dusting and scratching. The last, let's go over here please. Come over here. The last part of the laser system is a component handling system. In this case, it's a 3-axis CNC table. You see actually the laser is equipped with a standard nozzle system which is being used for surface treatments, for welding. Means it's one with a focusing mirror, right? Yeah. You have here a CNC control table. You normally have 3 linear axes, X, Y, and the Z axis for focusing and defocusing the mirror. And in the case of any circular components, you additionally have rotating axis to treat any rotation symmetric components. By this CNC control table, the movement of the workpiece is controlled and the position to the focal point of the laser is being controlled. So you can also have a 3-dimensional treatment with the Z-axis following some surface rips or contours which might occur on real component surfaces. Just go there. First here. So what you see here, that's a powder feed system for the supply of any powder type additional materials for laser alloying, for laser cladding. We have a typical wheel feeder where powders, or with 2 feeders also mixtures of different powders, can be fed over a nozzle system directly to the surface of your component where the alloying or cladding process will take place in. The powder feeder itself can be regulated very fine to achieve very well-defined powder feed rates. The powder feed itself you have to measure because every powder has different densities. Aluminium powder is much lighter than steel powder, so you have once to measure for every powder feed rate. There's a rate in grams per minute. You normally just can adjust the rotating speed of the wheels and the gas flow in this powder feeder. But with this equipment you can achieve very fine powder feed rates, also suitable for alloying processes. So that's, I think, all about the equipment for the laser process himself. Another thing was mentioned by John before. Every type of laser treatment, some safety precautions are necessary because the laser is always, or this type of laser is working in the infrared wavelength, so you don't see it. You just feel it when it hits your skin or your eyes, and then it's too late. So all laser workplaces are normally equipped with protecting walls or completely enclosed in some cabins, and stuff which is working there always needs at least to protect your eyes with special designed protecting glasses. So this little protecting glass looks very special, but the companies who are selling this earning a lot of money with it. You have to know that, especially for the infrared wavelengths of a CO2 laser, simply plexiglass, I think the chemical thing is polystyrol, I'm not sure. This is normal plexiglass. It's nearly 100% or 100% absorbing the laser beam. So this protecting glass for CO2 lasers are simply made of plexiglass, and the companies are selling this for approximately 300-400 euro. Is some hundred Maltese lira, I think, 200-300 Maltese lira, I think. Yeah. So the companies know how to earn money with it. The only thing they do is that they write the wavelengths where these glasses are suitable for. In the case of other laser types, you need some more specialized glasses, but in the case of CO2 lasers, it's mostly simply plexiglass. The next step is to show you just a little more practical examples of laser treatments. So I think here we have some nice exhibits on laser cutting. So complex geometries cut out of steel, maybe aluminum, I don't know what it looks like. Stainless steel, I think. And some types of surface treatments. I think this looks like some simple tries on cladding. I think it was be done with wire cladding, as far as I know. I think the claddings were wire claddings?
Yes, that's right.
Okay. So where you use additional materials in the form of wire. And I think here you can see some examples for real components to being treated. Should it be hardened or remelted? Hardened.
In that case, it's hardening.
So
This case should be very familiar because it's... That's right, one of yours.
okay.
This is a test piece which was sent to us for attempting to rebuild damage. We're still
Okay.
working on the procedure
yeah.
which we could follow
Okay.
for this.
I think these are some of the examples. I think I will take this off. You can have a look on this. And the last thing in our demonstration now will be to present you some different or two different types of surface treatment. You will see simply laser hardening. You can see that especially the surface quality will not be affected very strong by this hardening process. And contrary to this, you will see the laser remelting and see also the good or bad quality of a laser remelted surface. Okay.
This time round we're going to use the laser. Now I'm putting on my glasses not because I want to be safer than you, but just in case I have to go around this way for some reason, it's better to be safe.
So it's not really spectacular, but you see a little oxidation there. The component is cold now, and if you would do a metrographic cross section, you should have a certain amount of some 100 microns to be martensitic hardened. And you can feel it, there's no modification of the surface quality after the laser hardening.
You can still see the grinding marks
Yeah?
still present.
So you always retain the original surface by this process.
Okay.
We do now what? This
Now again, surface hardening, but this time not just one run, but a small surface area. Know that whenever I go to handle some component over there, I always switch off the shutter. I don't want anyone messing around and switching on the laser.
areas. This way he is doing it now with single tracks. Is always a problem because with the following track you have a heat affection of the previous track. So you can have a softening in this overlapping region, or in the contact regions there. So preferably you would do this type of treatment with a beam forming which allows you, as I said, a wider laser beam, a broader laser beam to do it at once. If it's not possible, you have to take into account that you might have a softening in this overlapping areas.
Again, I'm going to check the run. back. In fact, I made an error through all. What's this? Here, give me. Or bring it, okay. Can it be programmed by directional? By directional?
It can be, yes.
Save time.
But sometimes it's a problem because when you go there and then go back, this region is much hotter than there. Yeah. So it's more uniform if you do it this way.
This time it's hotter because there's more heat.
More power being absorbed there.
It's not overlapping.
Okay. No, it's not exactly overlapping.
Not overlapping.
There's a small
Just-
space. You also have to be careful because if you carry out one run for hardening, the second run could temper the first one, so it could reduce the effect.
So-
So
right.
you have to verify all your parameters,
Yeah.
the gaps, the distance, the continuity. You may have to stop to wait for cooling.
Measure here or hardness, you see the difference?
I think we'll be doing this in the other group with Bertram, if I'm not mistaken.
Right there.
Usual check.
Well, see something there?
There you go. It's
see
not
it.
very clear to see, but it's being hardened. Okay? In this case, it's very important to be careful for these, for example, thin features.
Yeah.
Because if you are trying to harden this area,
might
and if
deform
you,
them.
that's right, you might use too high a power. These are also higher up, so the beam would be more near to being focused than
So
at the
higher
bottom
power
down here.
density, yeah.
So you have to be careful because you could remelt those areas. And remelting can be useful, but in this case would not be useful.
Because
not
Because
about-
remelting will
What
be.
about the walls?
Uh-huh.
I mean, it's round. So
Yes.
Now the laser's beam and the walls are affected by the laser. walls.
Yes, in fact, you would have hardening across the semicircular section. Okay? Yes.
Not the wall jacks, but the wall.
The beam is not touching these edges, it's just within.
No, what I
If
mean
you-
is,
uh-huh.
is it focused on the center here?
No, it has to be out of focus because if it were directly focused, you would probably cut the material at that rate or melt it.
so
You
just
definitely
had,
melt it.
has adapt the beam diameter and the power to
Yeah, so-
this area.
Okay.
Yeah.
You have to be a bit careful because I think I understand what you're saying. There's a different focusing at the
Focusing,
bottom
yes,
and at the side. So you have to select your parameters to perform a process which is suitable across the whole section.
So when we say we're cutting and when we say we're hardening, we're just varying the focusing of the laser beam.
Yeah. The power density by
This-
focusing.
That's right. For cutting, you'll be focusing within the material itself and using gas to remove the melted material, the molten material.
So generally for welding and cutting applications, you're working in the focal point of your optics, and for any types of surface treatments, you are working out of focus normally.
So when you have hardening treatment, this width
Yeah.
with one cut, you have to unfocus. and
Yeah,
then-
but sometimes you cannot reach the necessary power densities because you're limited. Yeah,
by the power of the laser.
right. So you're limited in
That's why
size.
the laser power according to the focus you are using.
Right. You can help a little bit by beam shaping, shape it to a line, but you're also limited to several centimeters, I think, in this. Otherwise, the power density is not high enough to achieve an austenitization of your material. So that's what I said in my presentation. Laser is not really a tool for hardening big surface areas. This you can easily do by other induction heating or something. It's more a precise tool for precise heating or precise hardening of parts of your component, like shown here in this tool there.
Now this time I am also changing the power.
So now we're working with higher power densities to achieve a remelting, complete remelting of this cast iron material. Do you have any shielding gas there?
Yes.
Or-
Yes.
Otherwise I was afraid of your mirrors. So, cold, hot, you think? But yeah. When you no, not really. You feel a little modification of surface, but not very much. So there's also one big advantage of the laser process is that still in the remelting process, the surface quality is quite good. So you only need a very small final finishing, like bit machining or mostly only a bit grinding. Yeah? The dimensional stability in this process is very good in the surface quality.
You're also
Okay.
improving the surface quality.
Pardon?
You're also improving the surface quality.
You can.
Well,
If it's rough before, you can be better after laser
In
treatment.
terms of hardness, I mean.
Yes, that's true.
In terms of
you
hardness.
do
Hardness,
it's
yeah,
again
yeah.
a hardening process.
So,
But
what you,
you have to be careful because you practically always have to machine if you want a good finish after the melting.
So in this case, remelting is you mean you go deeper for hardening, deeper
the depths might approximately similar.
to the one we did before.
Yeah.
The one just
But in the hardening process, you do it without remelting. But the hardening also, if you have hardening with a low velocity, lower power densities, you also can achieve hardened layers of half a meter to a millimeter or something. And in the remelting process also, it strictly depends on your parameters. You also can have remelting depths in cast iron or steel of the same size. So it's just a case of power density in this case. The depth is nearly the same because it's by simply given by the heat conduction within the interaction time. Yeah.